Hi there. So this is the rig that I built over the last days. It's a thermos flask with a motor, and in the bottle is this metal steering thing. And if I put power on the motor, then this will turn around. This is a thermometer temperature sensor, and so if I put electricity on this motor, this will spin around. And the idea is to demonstrate how spinning that thing around will heat up the water, to demonstrate that by measuring the temperature. But of course first we have to determine, let's say, and then we basically are demonstrating the conversion of the power of the rotation into heat. Hi there, so we're back in my lab. We have built the whole device. The electromotor is turning quite stable. It's mixing the water in the thermos flask. On the screen you can see that I'm measuring the temperature. It's now 13 degrees Celsius. That's what the sensor outputs. I've got a little, let's say, a breadboard here with some old chips, but this is the one that I'm using. It's basically, this is the interface with the temperature sensor. It puts it out through the serial cable. I've been making the calculations for the power that is dissipated. So we measured without water 130 milliampere, with water 250. The difference is 120. If you do 120 milliampere times the 8.43 volt, you end up with a power of 1.0116 watt. That power has to go somewhere. It's being consumed electrically, and so it will be heating up every part of the electromotor, maybe the wood and the water inside the thermos flask. And so I've been looking into the energy needed to heat water. To heat 1 gram of water you need 4.2 joules if you want to heat it by 1 degree. We have 675 grams, milliliters, because 1 liter is 1000 milliliter, and it's also 1 kilo usually, so you have 675 grams of water, which would need 4.2 joule for each gram to heat up 1 degree Celsius, so that is 2835 seconds that it would take if you put in 1 watt. If you divide that through 60, then you get 47 minutes to heat the whole thing 1 degree Celsius. But we're now seeing a little increase already to 14. Maybe it was 13.9 degrees Celsius, but technically it would have to take an hour from now that the temperature of the water reaches. So we'll wait and see. Well, it's a little bit later, and I have 2 problems. One is that apparently the way I mounted this, there's lots of resistance of the motor as it's turning around. So if I leave it like this, it's slower. It's almost twice as fast. So a lot of the energy is going to be lost somewhere between the motor and the steering device. So this is another iteration of the design of the test rig, because this part here, the axle was basically digging itself into the wood and getting stuck, so a lot of energy got dissipated at that point. Of course I didn't want that. And now it's turning away at a slightly higher speed. I'll leave it like this for a while. It's now 15 degrees. If this energy calculation that I made earlier is correct, then it will still take about 50 minutes to get through to 16 degrees. I'm not sure if you can read this. It's very flashy, but it's still 50 degrees Celsius. So we'll wait a little bit, and hopefully this works. It's not the most optimal way to transfer rotational energy into heat, but it certainly is a good demo, I think, of the principle. because the search then becomes how to most efficiently do that and how to deal with the effects of taking torque of the axle. And that's a whole story, a whole nother story that you have to think about. So, well, we'll see what happens. So I now put the axle a little bit off center, and you can immediately see that it turns a little bit heavier, and you hear a little bit more water noises. So I think that's a good sign, because you know, if you just let it turn and it creates a vortex and that's stable, then I don't think you're losing lots of energy in the water. This is just to make this experiment work. I'm thinking of quite a number of ways in order to in which I can improve on this design, and I probably will. So stay tuned, and we'll continue this. See what happens. It's 15 degrees Celsius on the screen, and well, we'll see. So about half an hour passed since I last filmed this, and lo and behold, it's amazing. The temperature has gone up 1 degree Celsius inside the thermos flask, which is about what I expected. It's not that it's gotten hotter in the room, it's actually still quite cold, even though it's warmer than 16 degrees. But the top is quite well closed, so I don't expect much heat to enter the flask. But we'll keep this turning for another hour, or another couple of hours, and then the temperature still should move up. And this might look like a very small achievement, but and it is, of course. But if this was a big water tank of cubic meters, and there would be a big pedal in it churning away, then of course it would get warmer and warmer, and that heat would be stored in the water. And if you insulate the water tank enough, then that could last quite a long time. And so 16 degrees. So it's a little bit later, and I have to still check if it's the room temperature that drove it up, but we do have 17 degrees Celsius now. What I'll do is I'll stop the motor and basically take out the temperature sensor, and then see where the wire is here, and then we'll leave it, and it will of course show us what the temperature in the room actually is. I'll take this out without ruining anything. So this is the this is the very small pedal. It's much smaller than it was before, so that's of course another reason why it takes long. But what it does, it basically gets the water to churn inside the thermos flask. I cannot look inside; it's too dark. There's water in it. That you probably can see that, and it's still rotating, as you can see. But I guess this experiment I think is can be considered successful. And oh, you can see actually that, and that might be a degree more. Oh, there, it's back on 17 degrees. So really the water is 17 degrees. The external temperature is 14 degrees. And so it actually got 1 degree warmer, while the outside temperature got about 4 degrees lower. So that really means that the heat has to come from the rotation, because there's no other heat source in the thing. You could say, well, maybe the temperature sensor is the heat source, but then it wouldn't be a very good temperature sensor, of course. So the challenge is now to find a different way to do this. Maybe, or do a little bit more calculations. The nice thing about a pedal churning in water is, of course, that it's really low tech, that it is not going to wear out very soon. You have well, boat propellers, for instance, they do a lot of churning in water, and they don't well, they do wear, but it takes years for them to show damage. usually, except when something hits it, of course. But well, that's the next episode. Thanks for watching. Until now.